this lecture is to get a little practice working with kets and bras written in the column and row vector form, and also to represent operators as matrices acting on our states, our kets and bras. So to begin, let's just start the things here. Let's just look at how we represent our ket vectors as column vectors. So I'm going to come up with some arbitrary numbers here. I'm just calling them A and B, like that. And we want to think, okay, what's the corresponding bra? Well, we just flip that, of course. And this is a row vector with A star, B star, complex conjugated. They may be complex. And then when we take the inner product, of course, we get psi on psi is equal to row B, A, B. And now remember how this works. We take this component times that component, and then add that to this component times that component. So we get, when we do that, we get A star A plus B star B. Okay, so that's how we do it. Now, so that's, we could do, and again, if we had different vectors, this doesn't have to be real. This isn't, so again, if I had, say, phi acting on psi, let's just make up some different letters. Let's say C star. It doesn't. We don't have to put the stars here, but we'll put them anyways, just for comfort. A B. We see in this case we get C star A, the first components of each, plus D star B. That's if they're different. Okay. Now, what we're interested, though, what we want to get to is how do we write our operators acting on this? So operators are going to be central to our study. So we want to think about an operator as a transformation of one state to another. It can be a transformation from one state to the other. So I'm going to do this generally. We're going to talk about some ket phi, which is equal to some operator, we'll just call M, acting on the state psi. Now, if you're familiar with linear algebra, this is probably, hopefully, familiar. But we're going to go a little further because we have to, the complexity will be the complex nature. No pun intended. Well, I guess there was pun intended there. So, but let me come up with a form for M here. So let's just say M is equal to, now I'll put the elements in here, M11, M12, it's row then column, 2, 1, M, that. And they may be complex, so we have to be aware of that. So that when we do this, I'm going to actually zoom in here because we're going to need some room here. So we'll make this down here. So that M on psi, now written in the matrix row and column vector formalism, is going to be this 1, 2, 2, 1, and 2, 2. And that's going to act on what we called A, B. So all that is going to give us, again, how we do this, I'll just do the first one here. So that row acts on the first element, and then this one acts on this one, and we add it for that top part of the vector. So that's going to give us M11 times A plus M12 times B. Okay, that's the top one, and then the bottom one again is going to be the M21 times A plus M22 times B. And that's how we have, and that's the transformation. So this is equal to phi, and depending on the values of M11, M12, and so on, we'll get various a change in the state possibly. And of course, you can see that just quickly. You can see that if M11 and M22 were equal to 1, and M12 and M21 were equal to 0, we would get the same vector back. That's what we call the identity operators, just 1's on the diagonal and 0's on the off diagonals. Now, here's where what we want to do is we want to figure out how to represent bras now. And this is where it gets tricky. And we're going to introduce a little bit of operations on the matrix to show how this works. So what we want to do is, so this was, remember, this was equal to phi. What we're interested in doing is finding the bra vector. So first of all, we're going to do this in two ways. First, we're going to go to our result here, which is here. And we want to write this, again, this is phi. Put that up here. we want to write the corresponding bra. So I'll just put an arrow here. So in this case, the bra, remember we turn it into a row. I'm going to go over a little bit. Yeah, let's go over here. So that's going to be equal, but then we take the complex conjugate. So it's going to be M11 star times A star plus M12 star times B star. That's the first component. The second one is, I'm going to do this even though it's off screen, M21, that's a 1, times A star plus M22 star times B star. Like that. Okay, so let's go back. Okay, so that's what we have. So what we want to do is we want to look at how a matrix operates on a bra. So this is the point here, and how we might transform one into the other. But we're going to use this as a reference. So we'll come back to this form later, because this is what we want in the end. This is what we need. But what I'm trying to get at here is we want to think about. So this is equal to phi. We want to, psi. We want to think, well, how do we do this by taking the bra? Well, it was supposed to be black. Of psi, acting on some matrix which should be related to M, of course, because we're just taking the bra here. I'm going to call it N just to keep it different. And then we want to see how does N compare to M. And the point is this thing here we want to equal to phi. And I might say like trivial why I'm doing that. Well, notice what happened when we multiply this out. So we're going to write the A star B. And now I'm going to have these new matrix elements here. I'm just going to make them a little lower so they fit here. N1, oops. That's an, let me just a second. That's an N11, N12, N21, N22. Okay? Let's, I guess we'll keep going here. So let's just multiply that out. So we get the first, so A star on the top, the A star on the top, and again, let me just emphasize this. This acts on this, that, and we add those. So we're going to have, on our first component, we're going to have N11, I keep writing M, N11, A star, plus N21 on B star. Let's move over a little bit. And now let's look ahead for the next one. So the next element is going to be N12 on A star plus, oops, I didn't want to do that, plus N22 on B star. That's our vector. Now the idea here is we're thinking about taking this whole thing here and turning it into a bra, like this. And so we want to think about what does that mean? Because we're just what we're doing is taking phi and flipping it phi. So we want to think about this as how does what matrix N acts on psi so that we get the bra of N. That's the idea here. So this is equal to that. So so what we need to do is compare the two results we have and see what it gives us. So let's see if we can fit them both in. Let me go right here. There we go. So now let's highlight some things here. I'll use a different color here. Let's go to yellow. So now we look, this form here must equal this form here. And so we read off what N11 is and so on. And then I'll use a slightly different color. This term here has to equal this term here, because then the bra they will match up, and this will define or show us what N is and how we relate it to M. So notice what that means here. So this says that N11 is equal to M11 star, and N21 is equal to M12 star. That's what there. And for the next one, we have that N12 is equal to N21 star. And N22 is equal to N22 star. So that means, let's kind of, let's put it here, and then we'll, so N is equal to M11 star, M2, M21 star, M12 star, M22 star. So now we can relate n and m. We say, oh, how are they related? Well, notice what happens. We've taken a complex conjugate of everything. So we take the matrix and we take the complex conjugate of the whole thing. But also we flipped around the diagonal here. Like that. So what we've done, these are specific processes on two different processes acting on a matrix. So what we're doing here, we're running out of paper here, is we're taking M. Well, I wanted to be black. Okay, let's go here. And we're taking the complex conjugate. That's the first thing we're doing. So what that means. So that's equal to, again, M11 star, M12 star, M21 star, and M22 star. That's the operation of taking the complex conjugate of a matrix. But the other thing we want to do is flip around the diagonal. So if we flip around the diagonal, this is what's called the transpose. And so let me define that here. So MT. What that means is that if we start, we're not taking the complex conjugate here. We're just saying M11, M21, M12, M22. So we're doing both of these operations to get N. So N is a combination of both of these, and that goes by a special name, which is called the Hermitian conjugate. So we define M dagger is equal to M, doesn't matter which order, but star transpose. And again, it's going to be of this form here. So the form is that. So you flip around the diagonal, and you complex conjugate everything. So this is called the Hermitian conjugate of the matrix. So what does that mean? Let's just kind of summarize this, and then we'll come back. So what we have, remember, so we had the vector phi is equal to m psi. We had those there. Okay, now what we wanted to do is form phi. So how do we know it? If we know the matrix and we know the column vector, how do we write that? So this is equal to phi is equal to, now we write it this way, psi m dagger. So then so what we're doing here is essentially, so that's how we relate the two. And some people like to write it this way, which is fine. We can say m like this, take the whole thing complex conjugated, or Hermitian conjugate, that's equal to, some people write this, but like that. But it's just how do we go, so it's like if we have an operator acting on a state vector, ket vector, how do we flip it so that so it's consistent to get the same bra? And that's how we do it, and it's this form here. Now there's going to be a couple of uses for this, or yeah, well, definitely uses for it. And the first one has to do with the time evolution of a state vector. So the state vector, we evolve in time by what's called the time evolution operator. So let's give a quick definition of that. So, well, not a definition, but we'll just write it down. We're going to introduce more formally later. But what it does, if we start with a state vector, say time t equal to 0, or any other time, but just choose it to be 0, we're going to introduce an operator here, which we'll give by the letter u. I think in Susskind he uses u dagger. Let me just double check that. No, he uses bold for vectors, I believe. Or for matrices, operators, I should say. Yeah, so there are different notations here, but we're going to use a capital letter to represent a matrix. And I'm going to put this here real quickly, T0. That's just telling us how much this time evolution operator, u, is going to move it forward in time. So that's equal to psi at time, say, t. Some later time. So you know what, at time 0, you apply this operator, it changes the state to a later time. And again, you're going to need to know things about u in order to do that, about the physical system. But right now we're just kind of abstractly defining that such an operator exists. The question is, what type of operator is this? Well, quickly we can actually find what it is by looking towards probability. So let's take a state, and remember what we said, because of our conservation or normalization of probability, I should say, we're always going to have for the state vector that let's do it time t, is equal to 1. Because remember, this incorporates all the probabilities. All the probabilities add up to 1. But we also demand that the probabilities normalize through time. Like that. And this just says that if we look at the system one time, we have a set of probabilities. They're going to add up to 1. We let the system evolve in time, and no measurement's been done. The probabilities are still going to add up to 1. They can't add up to anything greater, and they can't add up to anything less. Let's do the mathematics, but this property here is called unitarity, and this is a fundamental property of quantum mechanics. It's unitary is the other way to say, or it's unitarity is the general scheme. So let's look at what we just learned about how to write these matrices in terms of broad form, to take this one and represent it in terms of the time evolution operator. So notice, first of all, let's do the easy one. Let's do the ket vector. So that's going to be u. I'll just put this parentheses there. T. That's just telling us how far we're propagating forward in time. I'll call it 0. Okay. So that one, right? Okay, it's pretty obvious. But now let's do the bra. The bra, though, now we have to take the Hermitian conjugate of t, like that. So this is what we have. So now we can think of this different ways. So it should be obvious what this term in the middle has to be. Because if psi on t is equal to 1 and psi of 0 and 0 is equal to 1, meaning the probability keeps equaling 1, this thing has to equal 1, or the identity operator, technically. So this has to equal, let's go over here, it's equal to 1. I'm going to write it this way, which is equal to, depending on how many 1, 1, 1, 1, 1, 0, 0, 0. We're going to zeros on the off diagonal. That's the identity operator. So this form here is important. Let me go down. Oh, what happened there? All right. Okay. So let's just define this type of matrix or operator, if you will. Operator or matrix, the same. So first of all, let's just say u dagger u is equal to the identity. That's the definition. This is what we call a unitary matrix. We can write this in different ways. One is we could say u dagger is equal to, that's a dagger, is equal to the inverse. So when we have u minus inverse on itself, we get 1. So we could say the dagger is the Hermitian conjugate is its inverse. That's one way to say it. We can also say other things as well, but we'll leave it this. But this is we'll just write it this way. Actually, let's put 2 of them. But this type of unitary matrix is important, and again, for the reasons just stated, is that because the time evolution, outside of not considering a measurement, but before we do a measurement, the probabilities must add up to 1. And if that's the case, the time evolution must be unitary. So in quantum mechanics, that's the big thing. We say that QM is unitary in its time evolution. Now, what's left to be seen is how do we relate U to things that we normally think about in physics, and how do we express U so that we can actually do some calculations. We'll leave that for later. But right now, this idea that quantum mechanics is unitary is critically important. And also note that what we'll get to is that really the measurement process is a non-unitary process, which lies outside of quantum mechanics in some sense, as mentioned before. It's an abrupt change in the state. Okay, I think that's enough for now.